Today we are starting Chapter 7, Solving Linear Systems First by Graphing. Now, what a solution to a system of linear equations is an ordered pair that satisfies each equation in the system. Normally we're going to have two equations in our systems. So a solution is going to be a point, x, y, that's an ordered pair, that satisfies each equation. So what we're going to do to solve it graphically is we need to graph both equations and then find out where they intersect. So the easiest thing to do is to turn everything into slope-intercept form. So I'm going to graph the first one first. I'm going to subtract x from both sides and then divide by 2. So our first equation is negative 1/2 x plus 7/2, or 3.5. So I start at that y-intercept, 3.5, and then I go down 1 over 2. Now in this section, when I'm graphing, accuracy is extremely important. So we need to do our best to make sure that our lines are super straight. Now mine will probably not be because I don't have a ruler, but everyone should have a ruler that they're using for their graphs. Okay, the second equation, I'm going to subtract 3x from both sides. Divide by negative 2. So y equals 3/2 x minus 5/2, which is 2.5. So I start at negative 2.5, and then I go up 3 over 2. I make the line as straight as I can, and find where they intersect. Now this intersects at 3, 2. So what I need to do with that, because my line could be not straight, or I could have ended up curving it or something, I need to test my solution. So if I got the intersection point of 3, 2, I have to plug that into both functions, and I'm probably going to use the original functions because they don't have fractions. I'm going to plug it into both and make sure that it works. So 3 plus 2 times 2, we want to know if that's equal to 7, which it is, so that one works. And then 3 times 3 minus 2 times 2, we want to know if that's equal to 5, which it is, so we know that 3, 2 is in fact our solution to the system. Okay, so summing up what we just did, we need to graph both equations in slope-intercept form preferably. Okay, then we're going to estimate the point of intersection. It's not always going to end up on a perfect line, so we're going to estimate it. Then we're going to check it algebraically. Like we just did. A consistent independent system is a system that has exactly one solution, so it's going to intersect at exactly one point, just like our last system did. Okay, so we're going to do the same thing. We're going to graph each one and find the intersection point. I'm going to put it into slope-intercept form and graph. That was a little off, so we're going to have to estimate our intersection point. Same thing with this one. Subtract x, divide by 4. Okay, so obviously they did not intersect at a perfect spot, but it looks like this one was supposed to be the correct intersection point, which is 4, negative 3. And then we need to check it. And they both work. So we know that that was the correct intersection point. Okay, two more down on the bottom before we have our word problems. I'm going to extend the line a little bit on this one because the y-intercept is 10. But they intersect very clearly, so that's not too bad. The answer for this one is 1, 5. Our intersection point is at 1, 2 for the second one here. Okay, now we have our word problems. The Parks and Rec department in your town offers a season pass for $90. If you're a season pass holder, you pay $4 per session to use the town's tennis courts, but without the season pass, you pay $13 per session. Find a system of equations that can be used to find the number x of sessions of tennis after which the total cost y, including the cost of the pass, is the same as the total without a season pass. So if we're going to have two different equations, we're going to have one with a season pass, and we're going to have one without the season pass. So first, if we had the season pass, we have to pay $90. But that's just a one-time charge. But then we have to pay $4 every time we use the tennis courts. Without the season pass, you just pay $13 every time you use the tennis courts. So that would be our two equations. And that's all we have to do with that one. Next one. A business rents inline skates and bicycles during one day. The business has a total of 25 rentals and collects $450. Find the number of pairs of skates rented and the number of bikes rented. Well, first, they didn't give us this information, but we need this information. The skates cost $15 to rent, and bikes cost $30 to rent. We need that information because one of our equations is going to be just the number of skates and bikes, and the second one is going to be all of the costs of everything. So our first equation is the easy one. X plus y is 25. X is skates, y is bikes, and that's all we need to do because we don't know how many of each. Then the next one we include the cost, so it would be 15x plus 30y equals our total cost of 450. Then we need to graph. Okay, I'm going to go by fives on both axes, and it's best to use the same scale. Okay, so we need to get them both into slope-intercept form. It might actually even be better when we're using word problems to use the intercept method. So we just find the two intercepts. So this one, the x-intercept is 25, 0, and the y-intercept is 0, 25. It's actually going to be a lot easier. Okay, and then our other one, probably want to use the intercept method on that one as well. So if I put a 0 in for the x to find the y-intercept, that's 450 divided by 30. 450 divided by 30 is 15, so that's our y-intercept. And the x-intercept, same thing, if you do 450 divided by 15, you'll get 30. Okay, so our x-intercept is going to be right here, and our y-intercept is going to be right here. And we're trying to find that intersection point. I will have to kind of estimate, and if you have a ruler with the exact boxes, it's obviously going to be a little bit more accurate. It looks like it's at about 18.8. Oops, it'd have to be 7 because we need to have a total of 25. Okay, and that was 7.1, solving graphs.